If you have already met Byte-Pair Encoding, WordPiece is going to feel almost familiar, and that is exactly what makes it interesting to look at. It grows a subword vocabulary in the very same way, by starting from characters and merging small pieces together into bigger ones. But it changes one crucial decision along the way. Which pair actually deserves to be merged next? WordPiece, from Schuster and Nakajima back in 2012 and later made famous by BERT, answers that one question quite differently. Let us walk through exactly how it chooses and why that one change matters. The whole story lives in how WordPiece builds its vocabulary, so follow that loop once. It begins from plain characters, just like Byte-Pair Encoding does. Every word is spelled out into its smallest possible pieces, and the vocabulary at this early stage is nothing more than that base set of individual symbols waiting to be grown. Then, instead of just counting raw frequency, it scores each candidate pair on its own merits. Roughly, it asks how much merging this particular pair would raise the likelihood of the training data, which works out neatly to the pair's frequency divided by the frequencies of its two individual parts. Here comes the heart of it. The best scoring pair, and only that pair, wins the merge. So the tokenizer favors a combination that is genuinely more informative together than its two pieces were apart, rather than simply whatever happens to be common in the text. Finally, the loop simply repeats itself. Score every candidate pair again, merge the single top one, add it to the vocabulary, and keep right on going until you reach the target size you set for the tokenizer up front. So the sharpest way to see WordPiece is right next to its close cousin. The older method keeps it blunt and simple. At every step, it merges whichever adjacent pair shows up most often across the corpus. Pure frequency decides everything, which is genuinely fast and effective, but it never once asks whether that common pair is actually the most useful token to create. WordPiece instead merges the pair that most raises the likelihood of the data. That extra bit of math quietly nudges it toward merges that carry real information rather than mere popularity, and it marks continuation pieces on top of that. So a word like playing becomes play plus a marked continuation chunk, while greedy longest matching handles the encoding at the end. Strip it down, and three ideas carry the whole method. The merges chase likelihood, not raw frequency. The scoring rule picks the pair whose combination is most informative relative to its two parts. And that single choice is really the one meaningful difference from Byte-Pair Encoding. Continuations get a marker. Pieces that begin a word stay bare, while pieces that continue one carry a special double hash prefix. So a model can tell playing apart as play followed by the continuation ing. Greedy longest matching, and it turns up everywhere. At encoding time, it simply grabs the longest vocabulary piece it can from the left, then repeats, and this is the exact tokenizer sitting quietly under BERT, BERT, and Electra. Alright, let us lock in the essentials. WordPiece is a subword tokenizer much like Byte-Pair Encoding, but with a different merge rule from Schuster and Nakajima in 2012 and popularized by BERT. Rather than merging the most frequent pair, it merges the pair that most raises the likelihood of the training data. Continuation pieces carry a special prefix, so a word like playing becomes play, plus a marked continuation chunk. At encoding time, it greedily matches the longest piece from the left, and it is the tokenizer behind BERT, BERT, and Electra. If you like seeing where these methods quietly differ, that is exactly the kind of thing we unpack at standarity.com. See you over there.